we've seen that the derivative of a sum is the sum of the derivatives. Very nice and easy. The derivative of f of x plus g of x is just f prime plus g prime. You just compute the derivatives separately. And that the derivative of a difference is the difference of the derivatives. So if you have one function minus another, then you just take their derivatives separately and subtract them. Very nice and easy to remember. What about products? So if we have a product, is the derivative of a product equal to the product of the derivatives? Let's try one specific example. Let's let f of x be x squared and g of x be x cubed, because in this case we can actually compute the product by combining these two into one using one of our exponent rules. Now, if this works, does this prove that the derivative of the product is always equal to the product of derivatives? Of course not. This is just one example. So you can probably guess where this is going, because if this doesn't work, then we know that this statement is not true. So let's try. X squared times x cubed by one of our exponent rules is x to the what? That's x to the fifth. And then by our power rule, the derivative of x to the fifth is 5x to the fourth. So for these particular functions, the derivative of the product is 5x to the fourth. Now let's compute the product of the derivatives. We know the derivative of x squared is 2x. We know the derivative of x cubed is 3x squared. And when we multiply those together, what do we get? 6x cubed. So it was not the same. So the answer to the question is no. I hope you're convinced. We cannot do this. So if you have two functions multiplied together, you cannot just take their derivatives separately and multiply them together as we could when we were adding and subtracting. Multiplication is somehow more complicated, and we need a different way to do this, which is what we're going to develop next, this thing called the product rule. So let's do that. So here, f of x and g of x are just any arbitrary functions, not the same ones that we used in that specific example. Any old functions, f of x or g of x, we want to take the derivative. We can always fall back on our limit definition. So if this is our entire function, imagine that this function were called, say, p of x for product, we'd be writing p of x plus h minus p of x on the top here. So p of x, if this is p of x plus h, we replace every x with an x plus h. So I need to write f of x plus h, g of x plus h, and then minus the function p of x, f of x, g of x, all over h. Now what? Remember, you don't know anything about f of x and g of x. They could be any functions at all on the whole planet. So, for example, it's not true that f of x plus h is going to be f of x plus f of h, or that it's going to be f of x plus h. We have no idea what these functions could be. They could be trig functions, log functions. They could be anything at all. Yeah, this is a stumper. So, no doubt the first person who did this completely by algebra without using any geometry at all. But I find it easier to understand it if we do a little bit of geometry. So I don't know how you learned to multiply in school, but for us, when we learned how to multiply, they gave us a particular geometric shape, a rectangle. Maybe it was like a rectangle of 3 rows of 5 bunny rabbits. And then we, from that, understood that 3 times 5 meant 15 by counting up the number of bunny rabbits. So this picture here is going to help us rewrite that top of the fraction. So I've got a big rectangle here whose width is g of x plus h and whose height is f of x plus h. So the area of this big rectangle is this product here. The small rectangle, f of x, g of x, is this rectangle here. Therefore, the difference, what I've got on the top of this fraction, is this part here. This part that's not counted, and this part. So I can rewrite this difference up here by adding up these two areas down here. So let's see about how we want to do that. So let's first look at this rectangle across the top. Let's figure out how tall it is. We know that this whole distance here, the whole distance here is f of x plus h, and this distance is f of x. So what is this? Are you tempted to say something like h or f of h? those aren't correct, right? We know, can we all agree that f of x plus h in general is not the same as f of x plus f of h, and it's also not the same as f of x plus h. In fact, it's a very, very rare function that will make f of x plus h equal that. So really, the only way that we can write this thing up here is by taking the entire height, f of x plus h, minus f of x. So the height of this strip across the top is f of x plus h minus f of x, and the height of it is that, and the width is g of x plus h. So let's write that. So its area will be f of x plus h minus f of x. That's its height, and its width is g of x plus h. So now I'm going to double shade that one in to show that we've already counted it. And we have counted this corner over here, so we don't want to double count that, although it actually wouldn't make any difference in the final answer. So now I need to figure out this little strip here. So this strip is f of x units tall, and let's figure out how wide it is. Well, the entire width here is g of x plus h. This part is g of x. So this piece here must equal what? It must be, the only way to write it is g of x plus h minus g of x. The entire width is g of x plus h. This part is g of x. Therefore, this is the difference between the two. So I'm going to take the height of this one, which is f of x, and then multiply by its width, which we just figured out is g of x plus h minus g of x. And this is still all over h. And you're probably wondering now, what on earth are we doing? We're making the situation worse. We started with this somewhat clean thing, and now it's gotten messier. But do not despair. What you can now recognize in here is some things that look familiar. I've got an f of x plus h minus f of x over h. That should look familiar. I've got a g of x plus h minus g of x over h. That should also look familiar. So we can break this up into two different pieces. So make this first fraction here f of x plus h minus f of x times g of x plus h all over h. And then this one. Limit as h goes to 0, this stuff here. F of x, g of x plus h minus g of x all over h. And then we can further break this up. If I have two things multiplied together over a fraction, I can just rewrite that as this. F of x plus h minus f of x over h times g of x plus h. Whenever I do this in class, somebody always objects. So do you really agree that this is true? Imagine it for some numbers. If you had 4 times 3 over 2, 4 times 3 is 12 over 2, that should be 6. Is that the same as taking 4 over 2 times 3? Yes, it is. However, if you put this over h separately, you would not get the same thing as you had before. So this is the same as that. And then we can do the same thing here. We can make our f of x, and then the rest of this stuff over h. Because we're trying to get these things that we recognize, right? This is going to be our derivative of g. This is going to be our derivative of f. So we're almost there. So this whole first thing is just our definition of the derivative. So this is f prime of x. And this, we want to see what happens to this as h goes to 0. As h goes to 0, g of x plus h should approach g of x. Plus, as h goes to 0, what happens to f of x? Nothing. F of x doesn't care what h is doing. It doesn't have any h's in it. So that's just f of x. And what happens to this as h goes to 0? This is our definition of the derivative, except that the function's name is g instead of f. So this is g prime. So this is how we take the derivative of a product. So let's summarize this. This is called the product rule. And it says that when we want to take the derivative of f of x times g of x, we do not yield to the temptation of just writing f prime times g prime. We've all agreed in the previous chalkboard that that is completely illegal. That doesn't work. This is what we need to do instead. F prime of x times g of x plus f of x times g prime of x. So not quite as clean or simple as the sum rule, but not too bad. And because you're adding, the order doesn't matter, right? I've written in this order. If you had switched this term over here and this term over there, it would be the same. If you switch these two around, it would be the same. These two around, it would be the same. So as I said, probably the first person who did this did not do it by drawing any sort of chart here like this. The first person did it probably entirely algebraically. And let's see how that happened. Here I had this term and this term. I just had two terms. Here, if I were to multiply these two terms times this, I would get two terms. And this times these two terms, I would get two terms there. So here I have four terms. Here I just had two terms. However, two of these four terms are the two that came from up above, right? F of x plus h times g of x is that term. And then f of x times negative g of x is that term. So what are the two new terms that we introduced? The two new terms that we introduced are negative f of x g of x plus h and positive f of x g of x plus h. So really, as we discussed in a different week, often we are able to multiply by 1 in a clever way to help us out. Here we didn't multiply by 1, but we added what? We just added 0. So by adding 0 in this clever way, in other words, by adding and subtracting the same term, we were able to break this apart into something that we could work with. So many times in math, you either multiply by 1 or add by 0 in a clever way, and it gets you out of the troublesome situation that you're in. So this is the product rule. That's how we have to take the derivative of a product. Let's practice with that. So suppose we want to take the derivative of x to the 8th times 3 to the x. So that we really don't have too many options of different functions to multiply together, right? Because if I multiply like two power functions together, it's sort of silly to use the product rule. X squared times x cubed is just x to the 5th. We could just do it that way. But according to the product rule, what do we have to do with this? The product rule, so if I'm calling this part here my f, and this part g, and if I'm going to follow the same order that we wrote the terms up above, it says first I take the derivative of x. So for that we use the power rule, 8x to the 7th. And I just multiply that by 3 to the x. We don't do anything with the g. So this is saying f prime times g. And then, the way that we wrote it up above, or down below, we're supposed to take f, which is x to the 8th, times the derivative of g. And the derivative of g is an exponential function, so we use our exponential rule, 3 to the x ln 3. So this is f, and this is g prime. And you can see that it's not the same as if we had just taken f prime times g prime. Let's try one more. Square root of x e to the 5x. So we were going to need to rewrite this, right, in order to be able to use our power rule and our exponential rule. You might like to think for a minute about how you would rewrite that. Maybe pause the tape. So before we can use the product rule, we're going to rewrite this as x to the what? 1/2. And then this, we don't have a rule for e to the 5x. We only have something to the x, either e to the x or b to the x. So we have to do the same thing as we did a little while ago and rewrite that as e to the 5 to the x. Next week, we'll have another way of taking the derivative of e to the 5x called the chain rule, where you're taking the derivative of one function inside of another. We don't have that yet. So now let's take the derivative using the product rule. So the product rule says we take the derivative of one piece. So let's say that x to the 1/2, that's 1/2 x to the minus 1/2. And then we leave the other piece alone. So this is my f prime times g. And then we're just supposed to take f, x to the 1/2. And then the derivative of g, so for that we need the exponential rule. So we've got b to the x, so that's b to the x times ln of b. And as usual, we don't need to simplify any of these things. If you want to simplify them, that's great. Go ahead and do it. But for example, ln of e to the 5 is just 5. But you don't need to simplify if you don't want to. So is this how we have to take the derivative of a product? Do not just take f prime times g prime. We have to follow the product rule, f prime times g plus f times g prime.